everyone. We want to go over something called Green's theorem, which is one of the more important formulas in calculus. The idea is we're going to do a line integral over a closed loop, and we indicate that with the little circle on the integral symbol. So we've broken up this loop into two pieces, going from vertical tangent to vertical tangent. Let's call the lower piece y equal f of x1 and y equal f of x2. And we'll call the first path C1 and the second path C2. Now we're going to break this up into two separate pieces. We're going to do the m dx and the n dy pieces independently. So let's start with the m dx part, which I can now write as the sum of the two line integrals So when I calculate this line integral and I add it to this line integral, we will complete this loop. Now in doing so, because y is this function and y is this function, on C1 I'm going to replace y with f1, and on C2 I'm going to replace y with f2. So this will become the integral at this point of mx f1 of x dx plus mx f2 of x dx. And my limits of integration for the first one will go from a to b. And on the second one, we'll go from b to a. Now, I'd like to add these integrals together, but I can't because the limits of integration don't match exactly. But we know from Calculus 1, if I reverse the order of the limits, I will change the sign of the integral. So that means that this integration here will become from a to b minus the second integral. So now I can write that as one big integral at this point. And so the one big integral I can write would be the integral from a to b of m of f1 minus f2. It's getting kind of close together here. Now the next thing I want to do, I notice that f1 subtract f2, but f1's on the bottom, f2 is on the top. So I really like to reverse this order here. And in order to do that, once again, I'd have to change the sign. Now, this looks more confusing than before, except if I realize this piece here looks like a double integral that has been evaluated. Most specifically, that looks like a double integral that has been evaluated from f1 to f2. So if you stare at that for a moment, if I was evaluating this and replacing y with these quantities, I would get exactly this. But now working backwards once again, what would I have had to integrate to get it to look like this? I integrated something with respect to y to get it to here. So that means I just integrated from a to b, from f1 of x to f2 of x, of the partial of m with respect to y, dy dx. So again, if I think working backwards, I get from here to here. So this final result here we can summarize by just saying the negative of the double integral over the region in the xy plane of the partial of m with respect to y dA. And there's the first half. Now taking the exact same region but reorienting it this time to look at a function of x being a function of y to x be a function of y, going from horizontal tangent to horizontal tangent, and calling this piece C3 and this piece C4, defining this as x equal G1, this is x equal G2. It's the same region, but now I want to integrate in a different order here. So now we want to consider the loop n dy. So very similar to what we just did with the m, this is going to equal the integral C3 of n of xy dy plus over C4 of n of xy dy. Now in this case, I'm going from g1 for the x to g2. So I will replace the x's with g1 and g2. So this will become the integral of n g1 of x, excuse me, g1 of y, plus n g2 of y, comma, y. And my limits of integration for C3, they're going to go from C to D. And then from C4, they'll go from D to C. So just like before, I'm going to have to change the sign of the second integral in order to add these two together. So when I do that, this will become the integral from C to D n of g1 of y, comma, y dy, minus the integral from C to D of n of g2 of y. And like we did before, we can put this together as one integral of the difference. Now, just like we did before, this also describes the region in the xy plane, so this we can consider as being the antiderivative of something where we've already integrated n of xy, and we replaced x with, in this case, we're going from g2 to g1 dy. And like before, this is the result of an integration these of y, not of x. g1 of y. And in this case, it would have been the partial of n with respect to x dx dy. And once again, that is the region in the xy plane. So we can summarize this as the double integral over the region in the xy plane of the partial of n with respect to x dA. This is the second half. So the big conclusion here is anytime I have a line integral over a closed loop, it will equal the double integral integrated over the area of the difference in the partial derivatives. And what you'll find is almost all the time, this can become significantly easier than this, where trying to parameterize and break this up into multiple integrals might be very complicated, and this might be very simple. So let's do an example. Let's evaluate x squared plus y squared dx plus 4xy dy. And my curve is going to be the curve defined by y equal x squared and y equals 2x. So what that's going to do is give us this closed loop right here. This would be y equal x squared, y equal 2x. Now we could break this up into two line integrals. We can call this C1 and C2. We'd do two separate parameterizations. We would add the results together. This would not be terribly difficult, but would also be fairly long. So what we want to do instead is, if I find the partial of n with respect to x, okay, this being n, so the partial with respect to x would be 4y. The partial of m with respect to y, this being m, that would be 2y. So therefore, that difference is just 2y. So that means the value of my closed loop line integral is simply going to be the double integral of 2y integrated over this region. Now, in this picture here, probably easier to just make this into vertical rectangles. So the y limits would be from x squared to 2x. The x limits would be from 0 to 2. And that would give us, 0 to 2 of y squared from x squared to 2x dx, sorry, this would be dy dx. And then when we evaluate that, we're going to have 0 to 2 of 4x squared minus x to the 4th dx, which is 4/3 x cubed minus 1/5 x to the 5th, from 0 to 2, or simply 64/15, which is a significantly easier integral than the other one would be. Now let's do another example. I chose one that was very complicated. Now, our curve is going to be this circle, which means the parameterization would have to involve sines and cosines. So I'd have to change my x's to cosines, my y's to sines, which would mean I'd have functions of trig functions, and that would be very, very scary. But because this is a closed loop, I can use Green's theorem. So we'll start off by finding the partial of n with respect to x. In this case here, that would be negative 2x times the sine of y. Now let's find the partial of m with respect to y. We notice it's the same thing, which means the integrand that I will be using will be 0. So the value of this line integral, which is equal to the double integral over the region of 0. Now, strangely enough, we got an answer of 0. How is that possible? Well, if you recognize this statement right here means my original force must have been conservative. So this leads us to a very, very important conclusion, and that is, if F is conservative, then this is always going to be 0, because the conservative force vector means that the integral is path independent. Path independent means that it only matters where I began and where I ended. So if I begin and end at the exact same spot with a conservative vector, I should always get 0.